In this lecture we are going to prove Borsuk Ulam theorem for odd degree. So this you can find in Hatcher algebraic topology on page 174. So basically the proposition says is this. So you have an odd map f from the sphere to sphere. So odd map means that f of minus x is going to be minus f of x. So then the proposition says that if you have an odd map, this map must have odd degree. So recall that the degree map has to be between the homology groups. So what we are going to do is that we will show that degree modulo 2 is 1. So that will be showing that the degree is odd. So before we do the proof of this, we have to do some preparatory work for two sheeted coverings. So consider a two sheeted covering map. This is a projection map from y to x, and here the chain complexes have coefficients z modulo 2z. So z modulo 2z means just this 0 1. This we are going to denote as this field with two elements. So chain complexes have coefficients in 0 and 1. So that is, you have chain complexes of this form ni sigma I, where ni is just between 0 or 1. So you have this two sheeted covering map. So then we can lift a simplex here, sigma nx, to two simplices of phi, because it's a two sheeted covering map, say s1 and s2. So you have a simplex here, say sigma. So obviously the coefficient here is either 0 or 1. So since this is, we are saying this is a simplex, so it is 1 times sigma. So this you can lift to two things here. So this is in x, so you can lift it in y. So say s1 and s2. So again both of them have coefficients 1 and 1. So then we have a short exact sequence of chain complexes. So again you can lift this simplex sigma to s1 and s2, because by definition this is a standard simplex. It is simply connected. So you can lift it like this. So then you will have this short exact sequence. The reason you have the short exact sequence is so if you have s1 and s2 here and the coefficients are just in 0 and 1, so only possibilities here are for this chain complex here are for a sigma here and a sigma here. This is 0, s1, s2, s1 plus s2. So obviously we are lifting sigma to s1 and s2. So s1 and s2 both get mapped to sigma. Both get mapped to sigma. So obviously s1 plus s2 will get mapped to 2 sigma, but now we are working in f2, so this 2 becomes 0, so this is 0. So s1 and s2 is precisely what lies in the kernel of this map. So we will say that this sigma we are going to map it to s1 plus s2. So this sigma we map to s1 plus s2. So that gives us a short exact sequence of chain complexes. So you had this y two sheeted covering, this map here, so just s1 and s2 getting mapped to sigma, but then the element s1 plus s2, this will get mapped to 0. So you will say that this sigma just gets mapped to s1 plus s2 in y. So again you have this x, y, x. So this is the beauty of using a z2 complexes. So this short exact sequence will give rise to a long exact sequence. So this can be used for any two sheeted covering map. But we are working with sphere, so we have to transfer this problem to a sphere, and the standard two sheeted covering is from sphere to projective plane Pn. So from Sn to Pn. So this is the two sheeted covering we are going to work with. So once we have this two sheeted covering like this, we can use this right here. So this y is Sn and this x is Pn. So you have Sn, Pn, Pn. So this short exact sequence gives rise to this long exact sequence. So Hn, Pn, Hn, Sn, Hn, Pn. Then it goes to Hn minus 1 Pn, Hn minus 1 Sn, Hn minus 1 Pn, then Hn minus 2, all the way to 0. So from this sequence we can actually even compute the homology groups of Pn. So first of all we have to understand this long exact sequence, because this long exact sequence is what essentially goes into the proof of this statement here. So first recall that the homology groups with z2 coefficients will just is what we expected. For 0 it is f2, and this is also for Hn, Sn. So otherwise you see that in normal system this is just integers, but here we are using z modulo 2z, so therefore it is z modulo 2z. So this is what this is, and it is for everything else it is just 0 for I between 0 and n. So this we already know. So let us put this in here. So this is just our f2, this is going to be 0, this is going to be 0, this is going to be 0, and this is just f2. So f2 here. So now there are only two possible choices. So since we are working in f2, that is a field, either you have f2 map this group here, or since you're projecting from here to here, nothing extra is going to come here. So the only possible choices for projective plane is either it is 0 or it is this f2. So if it is 0, then you will have this chain like this h0 pn is 0. This will also be 0 because this is also h0 pn. So you have 0 going into f2 going to 0. So this cannot happen in an exact sequence. So it cannot be the case that this is 0 here, this is 0 here, because f2 cannot sit in like this, because there is 0 sitting here. So f2 has to be iso to either this or this, and this is non-trivial. So this cannot happen. So it has to be the case that this is f2, and therefore this will also be f2. So again notice that this HISN 0 for I not equal to 0 or n, and the non-zero terms give homology as this. So now from here we can show that for every I from 0 to n you have this f2 as the homology. And obviously since we are working with f2, the maps are either multiplication by 1 or multiplication by 0. If it is multiplication by 1, then it's obviously an iso. So since we have this 0 coming in here, this map has to be onto, and since this is just two elements, you have to multiply it by 1. So that is, this is an iso here. So if this is an iso here, it has to be multiplication by 0 here. So if this is multiplication by 0 here, there is a 0 here, there is a 0 here. So that means this map is a iso or multiplication by 1. So this f2 is also here. So notice that how we got h0. These two are h0 are same, so we have h1. So this is 0. So this map will go to here, which will become h2, and here will be h2sn. So this h2sn is 0 again. So this is an iso here, but h1pn is f2. So this is f2. So this map, this also has to be f2. So you keep on carrying it on. So then you will have inductively, then you will come to hn minus 1 pn here, which will also be f2, and this is 0. So this will also be an iso. So this will be f2 again. So this you will carry over here. So this is 0. So this is again an iso. So this will be f2 here again. So this is 0. This is f2. This is f2 here again. So again same reasoning. This will be f2 here again. This map has to be multiplication by 0, and this will be f2 here again. Or you can break this chain here and then see what it is going to be. But this is the process. It has to be an f2 here, and then you have to have an onto map here, and that will just make it possible. So using this long exact sequence, we can actually find out the homology for Pn, but we already know this homology of Pn. You can use universal coefficient theorem to compute this homology of Pn with these z modulo 2z or f2 coefficients. More importantly, we are trying to see here is that which maps are iso. So this map here we have to see is multiplication by 0. So this map here is iso, and all these maps are iso. So this is the information which will be useful. So let us rewrite this information into a long chain which we are going to use again. So this is the first iso we constructed right here. So this is our first iso. So then we had this iso going in from h0 to h1, h1 to h2, hn minus 1 to hn minus 2. So I minus 1 to I. So this is our second important iso. So then we also had this iso right here. This was multiplication by 0 map, which is right here, and this finally we had this iso right here. So we have these isomorphisms, and this is what we are going to use now to prove this theorem. So now that we have this sequence, we can work with our proposition. So we are saying we have a map from sphere to sphere. So obviously we have this map from sphere projection map to Pn, sphere projection map to Pn, and this is the map F we have right here. So this map here, this projection map we have seen induces this chain complex. So this short exact sequence. So obviously this map here will also induce the chain complex. Now this map F, which we are taking from here, this will make this square commutative. So say you have a map phi here. So this map here will induce the map between the chain complexes. So say this map is F delta for the simplices. This is a phi delta. This is phi delta. And these are standard projection maps, two sheeted covering. So simplices will lift nicely, as we have talked about before. So this top short exact sequence of chain complexes will give a long exact sequence just like this. But this long exact sequence we are writing here for this top chain complex. It's on the top. So this bottom chain complex will give this long exact sequence, which we are writing here like this. So this is our long exact sequence associated with this. And these map between chain complexes give these arrows, making this entire thing a naturality square. So these are all naturality square. That means basically natural transformations. So basically the map between chain complexes is giving the map here. So this top row is a long exact sequence associated with this. This bottom row is a long exact sequence associated with this. And then these arrows are going to give us these arrows. So first, we know both these sequences are coming from here, because this sequence just comes from this map or this map. Both of them are the same. So let us write down the isos which we have obtained. So this is h1pn to h0pn. So we have this iso here, this iso here, both of them coming from here. Again, this iso we are just carrying here and here, this iso here and here, and then this iso here is here and here. Okay, so now from h0pn to h0pn there's just a 0 cell here, 0 cell here. We have seen this is z2. You just going from here to here. So this map is easy to see that this is an iso. In 0 dimension it's just easy to see, just a point mapping to a point. So here this is an iso. So this is a naturality square. This side is an iso, this side is an iso, this side is an iso. So this side has to be an iso. So let us put this iso in a different color. So this will be an iso because of this iso. So we have to just construct this iso. So h1 is an iso. So from h0 you can see h1 is an iso. From h1 you can see h2 is an iso. So you have this inductive step. So this hi minus 1 as an iso would imply hi as an iso. Just like from 0 to 1 we went. So next square will be from 1 to 2. And then from I minus 1 to I. So this keeps on going to hn minus 1. This iso. This leads to, because this is iso, this is iso, this is iso, this will lead to this is an iso. So from I minus 1 to I. So 0 to 1 we showed, then I minus 1 to I, n minus 1 to n. And this iso we have right here, this iso here, rewriting it here. So this is iso, this is iso, this is iso. So it has to be the case. So this is a commutative square that this is an iso. So this is an isomorphism. Now we are working in, F2. So we are working in F2. So this iso means that this is just multiplication by one map. So this is multiplication by 1. So modulo 2, you still have this degree 1 map, and that is what we wanted to show.